Hello there. Today we'll be doing my majority elements using the umpire method. First, we will understand the problem, like what are in and outs, what we're looking for, what are some edge cases, and then we will match the problem. In this case, this is an array problem. And for array problems, there are a few things we need to match for. Generally, you can sort the array. You can use a hash map. You can use a two-pointer solution. And that means basically you start from two ends of the array and you work yourself in. And now lastly, you have the sliding window. Alright, the sliding window is where you start from one position and you move a forward pointer until it no longer meets your requirements, and you end the window and you start a new one. Okay, so with that, we will then make a plan for how to implement this solution. We'll implement the solution, and then we will review whether the solution works or not, and then lastly, we will evaluate the solution for time and space complexity. Alright, with that, let's get started with the understanding. Is it possible to have a no majority element? And the answer here is no. It is not possible. You will always have majority element. All right. Is there any other edge cases that you can think of at this point? I can't. I'm gonna pause. So I think that's all the edge cases here. There are no edge cases for this problem. And what happens if we sort the problem? If we sort the problem and we line them up, we can get the majority elements using a sliding window. However, this will cost us a runtime of n log n, and I don't think n log n is the operation we would like. So this is for the sliding window and the two-pointer. And I guess the only runtime that we're looking for is that we're looking for a problem that we can solve in linear time, and we are looking to do this in n, and space is going to be n for hash map. So we're going to try to reduce our hash map solution to O of 1 space later. So here's the plan. I'll create a hash map. Then fill in the count and elements. Once count for elements is greater than n divided by 2, which is all the elements, we can return. However, this is only this requires O of n space. So to reduce the O of n space, there is a algorithm called the Miller's algorithm. Voting algorithm. And algorithm. I'm not spelling algorithm right. Hold on. Alright, there we go. Algorithm. Hopefully that's spelled correctly. So with this method, we're going to create a one candidate, and we'll do a +1 for seen and -1 for others. And once count is 0, then we will reset candidates to new number. With this, we keep the majority item in count, and that way we only have to store one item while we go through the entire algorithm. So let's say we have 3, 2, 3. Our candidate is going to be 3, and our count is 1. So with the next item, we see our number is 2, and so our count is now 0. Of course, we check the next one, and our candidate is still 3, and our count is 1. And so, as you can see, we only used one item to make sure that they have a majority of the counts. And that way, we have completed this particular problem. So let's implement the Boyer-Miller's voting algorithm. So first things first, we need a candidate. We'll set that to none. We get a count, set it to 0, and we go through each number. For each number, if a count is equal to 0, what we're going to do is set the candidate to equal to none. And we're going to do a count is going to plus equals 1 if the I number, like let's say, is equal to the candidate. And with that, else we do a -1, which is this line right here. So we can add that in here, and we can add this in here. Oops. All right, with that, we are good to go, and we can return the candidates. With that, because we don't have any items to review, the first one item will do that for us. So we can just run the code. It should work out pretty okay. Looks like we have a spelling error. Candidate instead of candidate. Let's run it again, and we should be good to go. All right. So with that, the space-time complexity is O of 1, because time, we only go through the entire list once, and we also only use one new item. So O of n for O of time, and O of 1 for space. Let's submit. And we are good to go. With that, we have solved the majority element problem in our O of n time and O of 1 space. And with that, I hope you enjoyed the video. Like and subscribe. If you want more videos, check the link in the description below. Thank you very much, and I'll see you in the next one.